Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe power plant and avionics certified. The date today is July 11, 2016. In this video lecture we are going to discuss the three laws of thermodynamics. The three laws of thermodynamics are described as following. Law number one, the law of conservation of energy. Energy cannot be created or destroyed in an isolated system. Law number two, the law of entropy. Entropy always increases in any isolated system. Law number three, constant entropy towards absolute zero. The entropy of a system approaches a constant value as the temperature of a system approaches absolute zero. There is also a preceding law of thermodynamics preceding the three, known as the Zeroeth Law of thermodynamics. This is technically the law of thermodynamics that precedes the three laws of thermodynamics, also known as the equilibrium of relevance of multiple thermodynamic systems, which basically states that multiple thermodynamic systems for which two are in equilibrium to a third shall maintain total equilibrium between all. However, the Zeroeth Law is a little more expanding and is not going to be discussed here for technical science applications. Entropy is defined as a thermodynamic property that is the measure of a system's thermal energy per unit of temperature that is unavailable for doing work. Absolute zero is defined as the lowest temperature that is theoretically possible, which is minus 460 degrees Fahrenheit below zero, for which all molecular activity of matter stops. So to decode what these mean in example form, the law of conservation of energy is exemplified inside of an internal combustion engine. You have a potential energy in the form of fuel, you have power lost to keep the engine running, and then you have useful power that's transmitted to the crankshaft. But all in all, the total energy in the system is constant. The total energy starts with the fuel, and of course there might be a starter adding some energy to start the compression, but once the engine fires off, the engine is maintained for power through the fuel. So the potential energy of the fuel is broken up into power lost to keep the engine running, and then useful power out to the crankshaft. So the ratio between the two is the efficiency. So the total energy involved throughout the whole close isolated system is constant. The energy is conserved. It's not created or destroyed. It's just constant throughout, although a majority of the energy in the fuel is being lost to keep the engine running and it can't use it, and the rest of it is harnessed into usable power. So a good example of the law of conservation of energy, which is the first law of thermodynamics, would be the concept of indicated horsepower, which is a sum of power lost to keep the engine running, friction horsepower, plus usable power output in the form of brake horsepower. But the total energy is constant because it's starting with the fuel and it's ending up as friction and power lost, and then whatever's left is power gained. The second law, the law of entropy. Entropy in lay terms is defined as losing molecular energy or systemic maintenance of a system. That is what entropy represents, the continual declining of a system's energy if it's isolated and no additional energy is added to it. So if you were to leave a certain isolated system, let's say a power system, leave it without any more energy maintenance to keep that system going, it would start to lose energy. Another example is electricity through a wire. The theory is that you could continually loop a electrical flow from, let's say, a motor to a generator, but then there's efficiency losses, and if you don't continue to put energy in it to overcome that loss, the energy that is decreasing, not available for useful work, it will continue to decrease the total energy in the system, implying that the entropy will always increase in an isolated system. So something from the outside has to keep adding energy to it in order for it to remain a constant. So in lay terms, entropy is just the deterioration of energy within a closed system. And then the third law is the constant entropy towards absolute zero. Now we know what entropy really is, and towards theoretical lowest temperature matter can exist at before its molecular activity ceases, absolute zero, there will be a continual constant decline of energy in the system the colder it gets. And if it could reach absolute zero, all molecular activity would cease, and then entropy would be the whole system. It would come to dematerialization or non-functionality. So these are kind of really broad laws, but they exemplify anything that has to do with heat, power, energy, almost everything you can think of. They have to obey the three laws of thermodynamics. The exception outside of the physical world, where heat, power, and fuel, or potential energy, is held as the energy source, not necessarily the source, not necessarily the loss, but the constant system of the known universe. The only exception to that, somewhere in the magnetic realm, there are some exceptions. However, that is under heavy debate, and it's not appropriate to mention those until certification of those scientific data are proven. Not to shun new discoveries, but to be very careful that there is an efficiency loss, and there are many exponential systems that interact with even magnetic flows of energy, which in the long run might, or more than likely will, interfere with a system's efficiency and useful output. A good example is when electric cars were coming out a long time ago. Inductive fields were understood, but they were not taken into account, and so many great developers noticed that inductive fields were causing exponential fluctuations greater and less than in closed systems that were theorized as highly efficient, but many unknown factors came into the play. And so it's very careful that you do not operate outside of the laws of thermodynamics when it comes to a power system. And so I wanted to just mention that because there's concepts for perpetual motion which always come to failure because the long run efficiency curves are not taken into account. And eventually, even if it was almost 100% efficient, or couldn't be anything more, but 30 to 25% efficiency is what you're going to get out of any power system in the real world. But there are some systems, if you go electromotive, at the motor, yes, 85% efficient, and electricity through a wire, 92% efficient. But there are some people that have brought the efficiency with their inventions to close to 99%, and it can be misleading that you are dealing with some type of perpetual motion, but over the course of time, it's always been proven that the system starts to lose energy, there's entropy involved, and you have to continue to add more energy to keep that system going. Even though they're extremely efficient, the concept of perpetual motion and the concepts of going to 100% efficiencies are theoretically in the drawing board, but when more and more information is applied into the actual real-world dynamics of the system, the three laws of thermodynamics come right back and prove the system is false. So it's all about operating in the real world and trying to maintain the actual logistics of a power system. So as long as the three laws of thermodynamics are observed and the losses due to entropy and efficiency are understood, then a system can be well maintained and supplied with the proper logistics for good maintenance, and or other more innovative designs could be brought forth focusing on entropy, conservation of energy. And the third law may or may not apply to the real world on the ground, but yes, when you start to come down in temperature, the entropy is held at a constant more and more, so it requires more and more energy to overcome that loss of internal energy in the form of heat and temperature. Thank you for watching this video, and have a great day.